All right, in this video, we are going to derive the C3h character table. And so for a lot of these sort of character table derivations, one of the nice things to do is to look at an example molecule in this point group. So this is boric acid. It's of C3h symmetry. And we need to derive all the symmetry operations in this character table as a very first step. Of course, we have the identity operation. We have a principal rotation axis. We know from the character table name we're going to have a C3. And I'm putting in these hat notations to show that we have, we're talking about operations here. So this C3 is going to go through here. And we're rotating this way. C3 means 120 degrees. You can imagine taking this hydrogen going to there, this hydrogen going there, etc. And so moving on from there, we can also have not a 120-degree rotation, but we can have a 240-degree rotation. If we do the operation twice, that's a unique operation. Now we can't do this 3 times because a C3 3 times is just bringing us back to where we started. It's a 360-degree rotation. What other operations do we have here? Well, we also have a horizontal mirror plane. That's where this H comes from, right? So that H, that mirror plane, is in the plane of this boric acid molecule. It's maybe not the clearest drawing. Let me try to draw it with some perspective. There you go. And so it's in the plane. So it's perpendicular because it's horizontal. It's a sigma h, and that's going to be another operation that we have. And then what other operations do we have? Well, we also have improper rotation axes. So these improper rotation axes are denoted by the term S. And so remember, like an S3 in this case is something we have. Anytime you have sigma H and you have a C, you might be likely to have an improper rotation axis. That's defined as doing, an S3 is defined as doing a C3 followed by sigma H. And mathematically, that does something different to the molecule. So you have to check to see if you have that. But in this case, we do, because we can do a C3. We already saw that we had that. And then we can follow that C3 by a sigma H. A sigma H for a flat molecule doesn't really do anything. It's just, cutting right through the center of all these atoms. So the top of each atom goes to the bottom of each atom, but no atoms remain unchanged. But that's going to be mathematically a unique operation. So we can write that down. And then we can think about what happens if we do, just like we did a C3 twice, what happens if we do an S3 twice? Well, that would be like doing a C3 twice followed by, and it's commutative, so any order you can do this, but C3 twice followed by 2 mirror planes. Well, 2 mirror planes is the same as identity. Because in a mirror plane, you took something from top, put it at the bottom, but then if you do it again, you took something from the bottom and took it to the top. We're talking about a horizontal mirror plane. Okay, so this term just drops out, this sigma h squared term. So this is just equal to, because identity is just equal to 1, equal to C3 squared. And we already have C3 squared. What about an S3 3 times? Well, that's going to be equal to a C3 3 times, followed by sigma h 3 times. C3 3 times, we already know from up here, was equal to identity, 360 degrees. And so that term drops out. And a sigma h 3 times, well, went from top to bottom, one time bottom to top, top to bottom. It's the same thing as doing just one sigma h. So an S3 3 times is not a unique operation, it's a sigma h. And then what about a S3 4 times? Well, that would be equal to a C3 4 times, followed by a sigma h 4 times. I think you can see the pattern by now. If you have an even number of flips, an even number of mirror planes, that just equals to identity. you have an odd number that equals to sigma h. So if you have an even number here, that term goes away, it's equal to identity. And so that just equals to C3,4. What is a C3,4? That's the same as a C3, right? Because a C3,3 times got us back to 360 degrees, and then we just have one more C3. So S3,4 times is just equal to C3. We already have C3 accounted for. What about S3,5 times? S3,5 times is a C3,5 and then a sigma h 5 times. Well, sigma h 5 times is a sigma h, is an odd number of sigma h. And so this is actually equal to, right, a C3,5 times a C3 twice, because we get to the same spot after C3 3 times, that's identity, times by sigma h. So this is actually S3 5 times, that's actually unique, because we never had this. We had the S3, if we think about back what an S3 is, right? An S3 was, we took this atom, go 120 degrees, for example, and then we do a flip. This one is now taking this atom and going 240 degrees and doing a flip. So those are different. It's a unique operation. So S3 5 times. What about S3 6 times? Just keep going here. Basically, you want to keep going until you get to identity. And S3 6 times ends up being identity. I can show you that. But why? Because an S3 6 times is equal to C3 6 times, and then a sigma h 6 times. We'll have an even number of flips there with our sigma h 6 times, so that drops out, it's equal to identity. And a C3 6 times is just spinning around 720 degrees, 360 plus 360, it gets you back to identity. So this tells us we're not going to generate any new operations. If you go try to do S3 7 times, you start looping back. So that's just equal to an S3 6 times an S3, right? And we know S3 6 times is identity. And so this is just equal to S3. So you start looping back. So these aren't unique as well. All right, so now we've generated our different character operations for C3H point group. Our first step in deriving the character table. And at this stage, we have to group them into classes. And here, it can be a little bit tricky, but basically for the CN or the CNH point groups, all the C's and the S's in this case are going to be in separate classes. And mathematically, there's a rigorous definition that I go over in other videos. But basically, there's no way that these are equivalent. It may seem that, well, you know, a C3 takes the atom this way and a C3 takes the atom this way, with how I just define things differently to go the other way. There's no way to, in this point group, if I define things to be the opposite way, I have to define a different axis system. And the mathematically rigorous definition of whether or not things are in the same class is if there's another operation in that point group that can interconvert those axis systems. And so a lot of times that's going to be like a vertical mirror plane or a dihedral mirror plane or perpendicular C2. We don't have any of those operations in this point group. And so for that reason, all of these operations are going to be in their own class. You know, identity is always in its own class. This is the only mirror plane, so that's going to be in its own class. I think it's clear that improper rotations are different than regular rotations, so those should be in separate class. The only weird thing is these ones, right? You might put those ones, group these together and group these together. And I'm just telling you, because there's no perpendicular C2, sigma V's, or sigma D's to interconvert these axis systems that would make these arbitrary, you have to put them in separate classes in this case. All right. So now what we can do is we can write our character table sort of skeleton. So we have C3H, we have identity, and now I'm dropping the hat notation. And the reason I'm dropping the hat notation is because now these are classes we've determined. and not just operations that we're talking about before. We have C3, we have C3 twice, we have sigma h, and we have S3 once, and S3 5 times. Those are our 6 unique classes, all with one operation in each class. If we have 6 classes, our character table rules, our first character table rules, see a previous video about character table rules that I have, means we're going to have the same number, we have to have the same number of irreducible representations. So we're going to have 6 irreducible representations. And the way to figure this out is the first irreducible representation is going to be 1s across the board. Always have the totally symmetric representation that's going to exist in every character table, 1s across the board. Okay, and then at this stage, what we can do is we can try to figure out how some functions transform. And so to do that, I'm going to draw an axis system. Remember, z is always going to be defined as our principal rotation axis. And I'm going to think about the z vector here. It's the first function I always like to try to test. And so what we do is we walk through one operation from each class. Well, each class here only has one operation, so we don't really have a choice of which one to do. And we think about how does the z function, the z vector, transform when we do an identity. And when we do an identity on z, it goes to z. And then we put the character by figuring out the matrix that describes this z to z transformation, which in this case is just a 1-by-1 matrix. And we take the trace or the character of the matrix, which is sum across the diagonals, where we have one component here. And in this case, we're going to get that the character is equal to 1, just that element there. So the character chi is equal to 1. And so we can say that the z vector is going to have a character of 1 here. We keep going. C3 is a 120-degree rotation, but it's spinning it this way, right, along that z vector. If we have a z vector pointing up and we're spinning it, it's still going to be pointing up 120 degrees. So z still goes to z. We write the same thing out. This time we're going to have chi of C3 equals 1. So we can put a 1 there. C3-2, same thing. Now we did a 240 rotation, but we're still pointing up. So it's still going to be a 1. Sigma h. So, for clarity, right, all these are going to have this exact same matrix. And we can circle those traces and get the character. Okay, what's the character of sigma h going to be? Turns out to be -1. Why is that? Well, z goes to -z, and our 1-by-1 matrix is going to be -1. Let's think about this. Remember, sigma h is a horizontal mirror plane. So it's horizontal to the perpendicular rotation axis. And so because of that, it's in the xy plane. And so that z vector is lying above the mirror plane. So it's looking at itself, it can look at itself in the mirror plane and reflect down below. So we're going to get a -1. What about S3? Well, remember what an S3 is. It's a C3 followed by a sigma h. And so that is a C3 just took z to z, and a sigma h took z to minus z. So we want z to z and z to minus z. Z went to z, well, we know z then goes to minus z. So that's going to be a -1. And What about an S3,5? Earlier in the video, we figured out that that was equal to C3,2 times a sigma h. C3,2 took z to z, and then we have a sigma h, which went to negative z. So that's also going to be a negative 1. So there we have it. That is how z is going to transform. And what's nice about that derivation there is we got a new vector, right? We figured out another irreducible representation. We use the words vectors and irreducible representations synonymously. Here we have 6-dimensional vectors. We're in 6-dimensional symmetry space because we have 6 classes, right? So that's abstract algebra we're dealing with here. But it's useful because of all the reasons that we've shown in other videos about what it can do to help us predict things in chemistry. So at this point, we want to test some other functions. And the next function I always like to test after testing z. A lot of times z will transform pretty simply because we define z as being our principal rotation axis. So the next one I like to transform is x. And so we do the same thing. Now we're thinking about an x vector. So how does an x vector transform? With each of the operations, one operation in each class. X is going to go to x. C3, x is going to go to what? Something complicated. Why is that? If we do a 120-degree rotation, it's going to spin like this, right? Spinning a C3 that way along the z, x vector is going to go in here. It's going to go into some linear combination of x and y. We have to use our rotation matrix to describe this. And that rotation matrix takes x and y, and you multiply it by, it's just some trigonometry, cosine 2 pi over 3, 2 pi over whatever your n value is. Or in radians. You could do it in degrees. Cosine 120 degrees is fine. And for the direction that we showed, we have a negative sign here. Negative, although it doesn't really matter if you put a positive sign here, you'll just go the opposite direction. All the math will work out. Negative sign 2 pi over 3, positive sign 2 pi over 3, and cosine 2 pi over 3. Now we take the trace of this matrix to get the character. And the trace of that matrix is just cosine 2 pi over 3 plus cosine 2 pi over 3, which equals 2 times cosine 2 pi over 3. Cosine 2 pi over 3 is negative 1/2. So 2 times negative 1/2 is negative 1. So underneath here, we're going to get a negative 1. We just did for C3. What about identity? Well, now we figured out that x is going into some linear combination of x and y. And so you have to keep x and y together. X and y are transforming together. We use this parentheses notation and listing them together. So because of that, we have to say, well, x goes to x with identity, y goes to y, and then we have the identity matrix that explains how we take xy going to xy. We take the trace of that matrix, and we get that the chi of identity equals the sum across the diagonals, 1 plus 1, which equals 2. And so we have a 2 there. All right. And at this point, we can keep going on. So for C3,2, we're going to have the same sort of matrix, rotation matrix here. But instead of having cosine 2 pi over 3, now we're rotating 240 degrees. So I have to rotate twice as much. So the chi, I don't have to write down the matrix just to save us some time. The chi is going to be equal to not 2 cosine 2 pi over 3, but 2 cosine 4 pi over 3. That's a 240-degree rotation. And so in terms of our unit circle, that brings us to the bottom left of our unit circle. So that's also negative 1/2. So 2 times negative 1/2 is negative 1. And so now we carry on here with our sigma h. So let's do that. So sigma h, well, With the sigma h, this one is not a rotation matrix. Remember we talked about this with z, but this sigma h is in the xy plane. So if we're thinking about an x vector or a y vector, erase that. Both these red and blue vectors, these x and y vectors, are in the plane. And so they're not going to change, right? And so what we're going to get is the identity matrix again. X goes to x, y goes to y, and we know what happens there. We get the same identity matrix. And so we're going to get a character is equal to 2. I of sigma h is equal to 1 plus 1 equals 2, sum across the diagonals. So I can put a 2 up here. We keep carrying on. Now we do an S3. S3, well, we're going to be doing a negative for x and y, right? We're going to be doing what is an S3? Let's just write that down. C3 followed by sigma h. So we're going to be doing a C3, which gave us a -1. And then the vectors aren't changing at all. So we know right away it's just going to be -1. Same thing with S35, C32, S35, sorry, is equal to C32, just as a reminder, times sigma h. Sigma h didn't do anything. S32 gave us a character -1, so we get -1. And so at this point, we can keep going on and deriving other functions. And the one I want to derive next is thinking about some d orbital functions, so some quadratic functions. And what I'm going to take advantage of is the fact that xz and yz are functions. And I know that z, doesn't equal to 1s across the board. So if I multiply z times something, z times xy, it's telling me those two are going to transform together, right? And they're not going to transform as the same thing. I mean, if z was up here and 1s across the board, then xz, yz would transform as gamma 3. But it's not. And what I can do is, since I just have 1s here, I can just multiply it through. So I'm going to get 2, -1, -1, -2, 1, and 1. So this is a really fast way of doing it. And, at this point, we're actually done, sort of. But there's a problem. We could test other functions, cubic, other quadratics, and you wouldn't get any other new functions. Problem, and I'll talk about this just as I do some erasing. Problem is that we have how many columns? We have 6 columns. We have 6 columns, but we only have 4 rows. Only have 4 irreducible representations. And that's violating our first rule of our character tables. If you go back to the character table rule video, it says that the number of columns and rows always has to be equal. Furthermore, there's another character table rule which says that the order of the point group, which is the number of symmetry operations in the point group, in this case 6, right? We have 1 operation in each of the 6 classes, has to be equal to the sum of the squares along of the dimensionality of the character table. The dimensionality just means the character underneath the first column, so underneath the identity operation. Okay? And so what that means is that in order to satisfy this rule, we should have 1 squared plus 1 squared plus 2 squared plus 2 squared right here, taking the sum of the squares, equals 1 plus 1 plus 1 plus 1 plus 1 plus 1 should equal 6. Obviously, that's not equal to one another, so we violated that rule. And so really we only have 4 gammas here. By the way, at this point, we might as well assign Mulliken symbols to these. We can do that at this stage. So let's go over that. Even though we have violated some rules here, we'll get to that in part 2 of the video, how to fix that in a second. But let's get our Mulliken symbols assigned. And so if we have a dimensionality of 1, that means we have a 1 underneath E. We're going to give this an A or a B. We give it an A if we're symmetric with the principal rotation axis. And that means if we have a positive 1 under C3 in this case. So both of these, we give it an A, and then we give it an E. These are just naming rules, right, for the vectors, for the irreducible representations. We give it an E if we have a dimensionality of 2. So both of these are 2. Now we can't have 2 things named the same thing. And so we use with point groups that have sigma h's, we use the prime notation. So we give it a prime if we're symmetric with the sigma h, and we give it double prime if we're anti-symmetric with the sigma h. And same thing with the e's. So symmetric, e prime, anti-symmetric, a negative number, double prime. Okay, but how are we going to fix this problem here? What we're going to do, and we're going to do this mostly in the next video, but we're going to break up, erase these bottom little things here. We're going to break up these e primes and e double prime vectors into 2 components. And so this e prime, we're going to cancel this out, cross this out, is going to get broken up into a component with 1 and 1. And the values of here, some of the values of here, the solutions here, 1 plus 1 equals 2, the solutions for the other ones are going to contain complex numbers, which have real and imaginary parts. There are no real functions that transform as these irreducible representations. But together, they describe something that is real, okay? So it gets into some crazy math. But when we do that, we're going to break this 2 into 1 and 1, and this 2 into 1 and 1. Then we'll be back to a situation where our character table rule is happy, right? In that we will have 6 1s across the board here. That will equal the order of our point group 6. So that's what we're going to do in the next video.